In this afternoon, we are joined by the Director PRL and several colleagues of PRL and the IAPT office bearers and on this WebEx platform. I welcome all of them. In the course of this event, I will invite some of them to conduct different elements of this program. The PRL IAPT lectures recognize wide range of topics related to physics, of contemporary developments, of national and international importance, and recognize the contributions of the Indian scientists who are taking a big role in various domains of physics and sciences of all these phenomena. These lectures cover various topics. So far we had 3 lectures which had topics right from planetary sciences to hydrology to high energy particle physics, which were delivered by Professor Anil Bharadwaj, Professor R.D. Deshpande and Professor Shubhavati Goswami. Today is the day for the 4th lecture to be given by Professor Abhijit Chakraborty. To tell the audience more about the PRL IAPT lectures and PRL, I will now invite Professor Anil Bharadwaj, Director, to make the opening remarks. Professor Bharadwaj, to you, please.
Thank you, Professor Pallam Raju. Namaskar, Susagatam, Kem Cho, Adabarze, good afternoon, good evening, good morning to all the viewers and listeners, and the panel members, the colleagues from and office bearers of IAPT, PRL, and other institutes. A very warm welcome to the joint PRL IAPT Dr. Vikram Sarabhai lecture. This is the 4th lecture. IAPT, along with PRL, initiated this lecture in the year 2019. And we are having this lecture every year in the month of February. Today is 11th of February. And incidentally, last year also, we had the lecture on 11th of February. This year, it's more special because of several reasons. Firstly, it is being organized as a part of PRL's 75 years of legacy and history. Secondly, it is being organized as a part of Azadi Ka Amrit Mahotsav, that is 75 years of independence of India. Thirdly, it is on a subject of exoplanet. PRL, as you all may be aware, is the institute who discovered the first exoplanet from India. And Professor Abhijit Chakraborty, today's speaker, is the scientist along with his team who discovered the first exoplanet from India. And fourthly, today is International Day of Women and Girls in Science. And of course, it is a weekend for Valentine's Day. So, with so many special qualities for today, we have an expert in exoplanet with us, our colleague from PRL, Professor Abhijit Chakraborty, who will be delivering his lecture on challenges and limitations of detecting exoplanets. And I'm extremely pleased that he has agreed to deliver this lecture. And he will be taking us to the journey of exoplanets through his experiences of challenges he faces and the way he has conducted this kind of observations, which are really painstaking to understand and discover exoplanets. So with this, I warmly welcome everyone who has joined us live on WebEx as well as on YouTube to the 4th PRL IAPT Dr. Vikram Sarabhai lecture. Thank you, and over to you, Pallam Raju.
Thank you, Professor Bharadwaj, for informing the audience about the initiation of the joint PRL IAPT Dr. Vikram Sarabhai lecture series, and also the importance of this year, especially as we are celebrating the 75th year of PRL's formation. Thank you. Now it is my pleasure to invite Professor K.N. Joshipura, who is a head of the department of physics and Professor of Physics at Sardar Patel University in Vallabh Vidyanagar, and past General Secretary of IAPT. I would request Professor Joshipura to briefly tell this audience about the activities of IAPT. Professor Joshipura, to you please.
Thank you so much, Professor Anil Bharadwaj. Greetings, namaskar, and majama in response to your Kemcho. It is a pleasure to thank Professor Anil Bharadwaj for the lead support he has been providing to this annual program series PRL IAPT Dr. Vikram Sarabhai lecture, which we started in 2019. And also greetings and all the best wishes for PRL at 75. This year, we in India are celebrating the 75th year of our independence. So many good things are happening. IAPT, Indian Association of Physics Teachers, is a grassroots organization devoted to initiatives, activities, and programs on physics education. We are working for physics teaching, physics teachers, and of course students, and also for science in general throughout the country. For the purpose of our activities, the programs and activities are conducted through 22 regional councils. The whole of India, we try to reach through regional councils. And for example, Gujarat is RC7, Regional Council 7. So on behalf of RC7 also, I welcome you all. IAPT was established in 1984, and this year we are celebrating the birth centenary year of the founding father, Professor D.P. Khandelwal of Kanpur, who initiated this movement. We are working through RCs, and they also conduct their own programs for students, teachers, also in competitive modes, and there are competitions for the teachers also at the national level. Our activities are also kind of at the national level, where we have the annual conventions. Our mouthpiece is IAPT Bulletin, and I'm happy to tell you that we have also established a good tradition. Every year, the lecture of the PRL IAPT speaker, this event speaker, is published in the form of an article in English, published by, written by the speaker himself, and that is published in our magazine called Pragami Tarang. Pragami Tarang means progressive wave, progressive wave. So that's the idea. I'm also happy to note at this juncture that this year PRL is an institutional member of our IAPT. So welcome to IAPT, and let us hope, yes, thank you so much. And let us hope that our collaborations and academic programs will continue. With this brief introduction, back to Professor Palam Raju. Thank you. Thank you.
Thank you, Professor Joshipura, for this information on IAPT and the various activities that IAPT is doing across the country for physics education through its 22 regional councils, and thank you for this information. I will now invite Professor P.C. Vinod Kumar to kindly introduce the speaker. Professor Vinod Kumar is presently the regional president of IAPT Regional Council Regional Chapter 7, that is Gujarat, and is also professor and head of the Department of Physics at Sardar Patel University in Vallabh Vidyanagar. I'm also happy to share with you all that he is also an alumnus of PRL. So Professor Vinod Kumar, over to you.
Professor Palam Raju, Honorable Director of PRL, Professor Anil Bharadwaj, Honorable Speaker Abhijit Chakraborty, Professor Joshipura, all I think R.D. Deshpande, Professor, all those who are known to me there and on this too. It is indeed a pleasure for me to introduce Professor Abhijit on this particular occasion as President of the RC07 of IAPT, as well as on this particular occasion of the IAPT PRL endeavor. This is the fourth such lecture series, and the speaker is really a worth speaker of an identity or remarks on the field of his research, and particularly in the discovery of the exoplanet, first exoplanet being detected from PRL in India. Professor Abhijit Chakraborty did his PhD from PRL. Then he went to, for a very few months or year, to TIFR, and then he went abroad to as a postdoctoral fellow at Pennsylvania State University, and then he continued few more PDF positions abroad. Later he returned back to PRL as a faculty member. In 2006 he joined as a professor at PRL, and presently he is heading the astronomy and astrophysics group of PRL. It is a great job that he is doing, and his contributions, particularly in the field of astronomy, exoplanet, many other optical device development, correspond to various facilities within India and abroad. It is really worth noting that his contributions are really great. With such a very luminous personality, agreed to give a lecture on this series. It is really welcome, and I appreciate his readily agreeing our invitations and ready for today's lecture. With this small introduction, I invite Professor Abhijit to deliver his lecture. Thank you all.
Thank you, Professor Vinod Kumar. Before I start my talk, I just remembered one incident that I met Professor Vinod Kumar the day I gave my PhD thesis review at Gujarat University. In the sense that I was after the review was over by the experts at the Gujarat University office, we went to the canteen for the tea and samosa with my advisor, Professor Anand Rao. And there, we found Professor Vinod Kumar was sitting there, and then we shared the chai and samosa with him. So, I just remembered that. So, it's a very, strange coincidence that today we are again meeting. So, yeah. So, okay, I'll start the talk now. Let me just share. Is it visible?
Yes.
Okay.
It's visible.
Okay. So challenges and limitations of detecting exoplanets. Okay. So see, when you look at in the night sky, you see stars, right? And if you take images like this one, you see star images. And usually in astronomy, what we do is that we take images. Like if you take images, then you see the colors of the stars are visible, and then what color they are depends using black body radiation theory, you can know what is the temperature of the star. If you want to do further study, you can do spectroscopy, then you can get the lines, spectral lines of the star, and then you can know whole lot of information from that. So that is what usually astronomers do. Like you get light photons from stars, and then either you do counting of photons, that is photometry, or you do distribution of photons with respect to the energy, that is frequency or wavelength, that is spectroscopy. Now, when it comes to exoplanets or planets on the stars, the situation is very different from this, because you really don't see the light coming out from the planets. And the reason for that is this. You see, if you look at this view graph, you see planets do not actually emit any light. They reflect the star light that is around which they are going. Like Earth reflects the sunlight, Jupiter reflects the sunlight. Okay. So if you see this is the is my cursor visible?
Yes, yes, it is visible.
Okay. So if you see, this is the star sun's black body curve, the sun's black body curve, and you see the black body curve of Jupiter and Earth, and you can see that the contrast difference, brightness difference between the Jupiter and the Sun is of the order of 1 billion, and while that of Earth and Sun is of 10 billion. So that means you have to see a firefly fly against the light of a lighthouse. So that is the challenging. And that slide will show you more vividly this challenge. You see, this is the Keck image of Epsilon Eridani. So the star is somewhere here. So it is coronagraphed. Okay, but the light is scattered through the corona, so you can see. Now you want to see something that is this faint somewhere here. So that is the problem. Okay, so when you can't see a planet, how do you know it is there? And B, how do you do spectroscopy? How do you measure what it is? So that is the problem. So now how do we do that? Well, fortunately, there are certain, indirect methods, like because science is very logistic, logical. I mean, what I mean is very logical and mathematics, highly mathematical. So that is how, like we apply those laws of physics to detect them indirectly. And I'll explain how. So what is astrometry and radial velocity? Okay, because if you consider a simple two-body system, you have like this. The two body will go around each other around their common center of mass. In case of stars, there are many binary system stars where two stars go around each other. Okay. Now, in case of planet star, the planet star, because the mass difference is very huge between planet and the star, the planet goes around the star, but the star wobbles around its axis because the center of mass happens to be very close to the center of the star. So this method can be easily applied to figure out the Doppler shift in the star's spectra due to its wobbling. So if the star wobbles, then obviously there is a planet around it. Okay, the other way method is, of course, just before I go to the transit method, the same thing, same wobbling of the star can be also observed using through astrometry from space-based telescopes over time, over a year time or so, how much the star is actually moving around its center positions like this. Either you observe it through spectroscopically or actually physically seeing the stars wobbling. Now, both of these are extremely challenging, I will tell you. Okay. Now, the next little bit easier, but still very challenging, is the transit method. In the transit method, what happens is that you have the, if probabilistically, if the orbital plane of the planet going around the star happens to be in our line of sight, then what will happen that you will have some kind of eclipse, like we have solar eclipse and lunar eclipse. So similar eclipse will happen, and when that happens, that is Earth, the star, and the planet going on the star. They are all in one plane. Okay. Then what happens? However, the planet size is very small compared to the star size, so it will there will be slight dip in the planet's star's brightness. And if you try to measure the brightness, deep in the brightness, you can get some references. So in following slides, I will let you know what references we can get. Okay, so basically what happens is that suppose this is your star with radius r, and this is your planet with radius small r. So as this small body passes in front of the larger star body, so it will block some light of it, and so you will get the dip in the brightness of the star. Okay, and so this drop is proportional to r square, the small r square, which is the radius of the planet, divided by capital R square. Okay, and so this gives, if you know somehow using stellar model what is the radius of the star, you will be able to find out what is the radius of the planet. And also by the period, because this is a periodic event, you can know using Kepler's law what is from the period, what is the semi-major axis, or how far the planet is from the star. What is the distance between the planet and the star? Okay. Okay, here is a small simulation showing what happens. So a smaller planet, when it crosses it gives a smaller dip. When a bigger planet goes around the star, it gives a bigger dip. Okay, now the question is that what is the probability of such an event happening? Because this can only happen if the orbital plane is along the line of sight. And this probability is quite small, less than 0.1%. But still, since there are millions and millions of billions of stars, so therefore, this less than 0.1% probability also is significant enough to look for planets around stars. Okay. Now, this is the radial velocity simulations, which basically shows that as the star wobbles, the velocity shifts, the sinusoidal oscillations, it shifts, and the corresponding these shifts in the spectral lines of the star spectra, because you don't see the planet, you only see the star. So by inferring the Doppler shifts in the star spectra, you are trying to figuring out what is the mass and the period of the planet going around it. Okay, before I get into the details of the radial velocity, I will just, as we know that we have recently major transit surveys have, space-based surveys have happened. Kepler started in 2009, then presently TESS is going on, and then in future Plato will come. So these two are NASA missions. Okay, as I said, is that there is a large amount of serendipity in finding out of planets around stars, because a priori we do not know which star has a planet around it. And to know this, what we need to do this, we need to have a survey strategy. And to have a survey strategy, what we have to have is that doing survey using radial velocity is very difficult, because you can do radial velocity with only one star at a time, and then you have to study that particular star for at least like few months or maybe a year to figure out whether there's a planet around there. So you cannot go into a survey mode like that. You need to, when you do a survey, you have to find out that you need to, at a time you have to at least survey about 500,000 or 100,000 or 200,000 or maybe 1 million stars, and then find out what it is. If you want to go into that kind of mode, then you can do transit surveys. Okay, so that is why the transit in survey mode, the transit method is applied. So you can see that in 2009, the first mission that went, and now it is over. The telescope is dead. Now it worked for almost 9 years. Is almost a 1 meter aperture telescope in the space, and it had a spatial resolution of 3.98 arcsec. Okay, the present one which is going on is a very small telescope. It's a 4-inch telescope, 4 4-inch telescopes kept in the space. Just a 4 4-inch telescope kept in space between somewhere between Earth and Moon, and each the total square degree it surveys is about 2304 square degree, but it has its spatial resolution is very poor. It is like 21 arcsecond per pixel, which means roughly spatial resolution of 40 arcsecond, and because of which its sensitivity is much poor than Kepler, but it is doing a much larger survey. Okay, similarly, in future, Plato will come up in 2026, which is again not very big telescope. It's again only 120 millimeter telescope, like a 5-inch telescope. Okay, and it will have like 24 such telescopes, and it will be kept at L2, second Lagrangian point, and it will work for, like it will look at a particular field for 2 years and look for planets around it. Okay, now what are the like what we have learned from such surveys from Kepler and currently learning with TESS is that like Kepler, for example, have been able to detect about 2662 about something around 2,700 planets. Okay, and TESS, for example, on return is expected to, it is still going on, is expected to discover around 1,700 planets, and the Plato is expected to discover around 4,000 planets, with only about 2 to 120 planets, Earth-like planets. Rest may be Jupiters or larger than Jupiters. Okay. Now the question is that if we have found out so many planets already, so like why these new missions are coming up, first, and secondly, like why we do them radial velocity. Okay, the reason we have to do radial velocity, because the transit method does not tell you the mass of the planet. It does not give you the mass of the planet. It only gives you the radius of the planet. Okay. So, and of the, like about 4,000 exoplanets that we know so far, only about, like 1,200 exoplanets mass is known. So we definitely know what those planets are. Like if you know their radius from transit, and if you know their masses, then obviously you know the density, and then from there you can easily infer whether it's a rocky planet or is a gaseous planet or something like that, because the density range is very, very strange. For example, Earth's density is about 5.5. So we know planets, like that ranges from almost very high density of 10, close to 10, to extremely low density like 0.1. Okay, so that is the zoo of exoplanets that we know today, and so the radial velocity work is extremely important to characterize the exoplanets, and for future studies of planets, whether to understand if they happen to be in the habitable zone. I will come in the slides what a habitable zone is in future slides. So then we need to know knowing the mass of the planet is extremely important. Similarly, as I said, that mass of the exoplanet can also be known through astrometry. Gaia is up there, but it can go, its limit is 25 micro arcseconds, and which can only detect up to hot Jupiters. So massive Earths or Neptune-like planets is not possible right now. The technology is not evolved enough to do measurements of sub-Jupiters around stars using the astrometry method. Maybe in the future it will probably happen. Okay, so I come back to the radial velocity method now. So it's, as I said, you have to simply apply Kepler laws, through which you can know that if when you measure, what you measure is basically the k value, the amplitude value, and the period of the amplitude. And so these two k and p value gives you the period the distance between the star and the planet, the semi-major axis, and the mass of the planet in terms of m sin I. So again, like the I is basically, if you see that if this is the plane of the sky, and this is the orbital plane, and the observer is along this direction. So the angle that subtends the orbital plane against the sky plane will be actually I, and so that I is being reflected in the sine I. And so if a transit will happen if this I is 90 degree, that is the orbital plane is in the line of sight of the observer, and so you get you measure, in that case what happens, you measure the actual mass of the planet. Otherwise what you measure is m sin. Okay, this is again, a very simple Kepler's derivation, from which we know that, okay, like we assume that like m1 plus m2 is equal to m1, because m2, which is the mass of the planet, is very, very small compared to m1, and hence the equation becomes simplified, and hence we are able to measure the mass of the planet. Now, someone asked that, they might ask that, how do you put the value of m1, that is the mass of the star itself? The mass of the star itself can be known from this mass luminosity relationship, through which you can know that given the luminosity of the star, what could be the mass of the star. And also we particularly do the spectroscopy also, that gives within 0.1, within an error bar of 0.1 solar mass, we can determine the mass of the star. Okay, so I have been talking of the habitable zone, and you see that, like this graph is, I'll be using this graph couple of times in this slide, because this is a very interesting slide, is that ultimately, you see, we are all interested to know, like how many planets we can discover in the habitable zone. We define a habitable zone planet by defining it as the planet distance from the star is right. So the temperature is within minus 50 to plus 50 degrees Celsius. Of course, this is a very straightforward. It's not a very straightforward calculation, because like the atmosphere of the planet will take a very crucial part, and that definitely will make sure if there can be a greenhouse effect and all those things. But still, like we have to start it from somewhere. And so here we are, and you can really see that this blue color here actually, this zone here is actually the habitable zone. Okay, and you can see the Earth is actually at the border of the habitable zone, and Mars is well inside the habitable zone. And still we know that Mars is so cold and Earth is relatively much more comfortable. Of course, people are talking of global warming and all those things, but still, this is still, we are still living on Earth, and it is still so far it's habitable. So the thing is that the planet's atmosphere makes a major role in defining the planet, whether planet is habitable or not, can be habitable or not. So so if you can make a Mars atmosphere, redefine Mars atmosphere in such a way, then Mars can be a very good habitable planet. Okay. Anyway, so so currently you can see that out of the so many planets known, we have very few that we have detected within the habitable zone. Okay, and I plot it here, and and the other thing that is shown here is what is the test limit, and what is the radial velocity limit. That if you want to detect Earth around a sun-like star at 1 U distance, your instrument spectrograph should be set with velocity resolution of less than 10 centimeter per second. Okay, and if you want to do habitable around, like MDOF, then maybe, like, because MDOF is a much cooler star. I mean, here you can see the star temperatures written. This is 6,500, 6,000, like this is MDOF 3,500, 3,000, like that. So here actually you can see the 20 centimeter, 30 centimeter, 40 centimeter. These are the K values limit of the instrument that can detect the planets. Okay, and this is also the reason why like detecting Earth planets so far has not been possible, because we have not been able to reach so far in the resolution limit of 10 centimeter or better. I will explain you in the future slides why it is so difficult and what is the limitations. Okay, this is another slide, the mass period chart, we can call it. So you have orbital period and you have M sin I, and the color of the dots are basically position. The dots are showing the planets, and their colors show around what kind of mass stars they are around. Say if it is blue dots are around M dwarfs, and green dwarfs around K dwarfs, and and uh, red and green are around sun, the sun type mass stars, one solar mass. So so you can see here also that, and this is the 50 centimeter resolution limit line. This is the 10 centimeter, and position of Earth is here. So like in terms of days on this, probably in terms of days it is here. So 365 is somewhere here, and 1 Earth mass. So he is here. So it is just below the 10 centimeter limit. And you can see this. So out of all the 4,000 stars that planets that we have known so far, most of them are above 50 centimeters. They have a cluster of here around here, because most instruments can do a resolution of 1 meter per second. We currently, the state of the art, we are pushing it down to like 50 centimeters to get fill up this area, but nothing is here, you can see. So that is the limit. Okay, so now with this introduction, I would like to come our effort in PRL about what we started in 2007 after I joined 2006 PRL. So actually, where earlier, like there was no very clear cut research activity going on in not only in PRL but anywhere in the country about exoplanets. So when I came back in 2006 from US, because US, I was working with a couple of groups which are like heavily active in exoplanet research. So I decided to start this program in India. So the first time, we started this, this program in India at PRL, because I was thinking which part, as I was applying for faculty position from US to PRL, I was thinking which place to go where I can get a proper, background, what you call environment for doing this kind of challenging research. After, doing some, like survey and all, I realized that PRL is the best place to do this actually. And so I decided to come back to PRL and started this program. And so the program is called as PRL Advanced Radial Velocity ABU search. The ABU word comes because we have an observatory at the Mount Abu, and basically, like we are looking at as we are looking at the sky, the stars from Mount Abu, so that's why Abu Sky Search. Okay, so abbreviated as PARS. Okay, this was the first high resolution spectrograph, stabilized spectrograph was made. I will not go into very detail into this. So it's a initial spectrograph, and I had designed it, then got the optics manufactured, and then put the system together and build the spectrograph, and so this instrument weighs about 1.5 ton. So obviously you cannot put it on a telescope. So it is kept in a temperature controlled environment, and the light from the telescope is fed through fiber optics. And let me tell you the challenges that starts from doing radial velocity determination is that you see. The spectral resolution normally we define as the if you take a spectra and if you see suppose an emission line or an absorption line, so typically its FWHM will define its resolution. Okay, as a thumb rule. So if you say you are working at 60,000 resolution, so at 60,000 resolution you will have the FWHM correspond to about 5 kilometer per second. Okay, roughly. So the question is then anybody will ask with 5 kilometer per second resolution, how we are able to go down to like 5 meter or 1 meter or some 1 meter. There what we do is that we run cross correlation because the stars have so much of Fraunhofer lines, like Sun has so much of Fraunhofer lines, though they have like more than about 5,000 to 10,000 depending on the spectral type of the star. They have this page of lines. So if the star is wobbling, then all these lines will oscillate like this. So when you do cross correlation at between time t1 to time t2 and time 3, you can go to at the sub resolution level by another 1,000 times. So it depends, of course, how many lines. If there are few lines, then it is not possible. If you can go to 1,000 times further resolution by precisely knowing what is the position of the star of the spectral lines by cross correlating at the spectra taken at T1 to T2 to T3 like that. I will future slides. I will be explaining it more carefully. The reason I am doing it here at this slide is that what is the challenging of making the spectrograph is this, that okay, you can get down to that level of precision, but when you have a spectrograph which dimension is about few meters by few meters and weighs about 1.5 ton, what happens is that you have the environment and under which the spectrograph is sitting. Any changes of 1 millibar atmospheric pressure will shift artificially the spectral lines by 100 meters per second. Any change of 1 degree Celsius across the spectrograph, it will again shift by 100 meter per second. So if you want to get down, let us say, forget about few centimeters. Even if you want to get down to 1 meter or few meters, you have to be stable to a level of 0.001, that is 1 milli-degree Celsius around a particular temperature. Say if it is 27 degrees Celsius, it should be 27 plus minus 0.0001 C. That should be the first condition. Second condition is the atmosphere. So it has to be atmospheric changing. So it has to be kept under vacuum. So which means that you have to have a very large vacuum chamber under which the spectrograph has to be fitted in, and then control that whole vacuum chamber temperature to a level of 0.001 degrees Celsius. As you know, all of us are physicists. We all know how difficult that is. So that these two are the main challenges. There are, of course, other challenges also. I will tell you that. Okay, so as I was talking on the vacuum chamber, so you can see the Paris vacuum chamber. So the spectrograph is fitted inside this, and this is the CC detector and the optics you can see inside the Paris vacuum chamber, and and so this whole vacuum chamber is kept under temperature controlled system, and for this Paris we have able to achieve about peak to valley about 0.007 degrees Celsius. So RMS comes down to about 0.002 or 3 degrees Celsius. Okay, so how does the spectra look? At the start of the analysis, you have this is the complete star stellar spectra from 3800 angstrom to around 9000 angstrom, which is the range of the bulb. So you can actually see the solid lines are actually the star spectra, and you can see these dots. You can see the blow ups in these dots. What we do is that we do simultaneous calibration. That is, there are two fibers. One feeds the star light, another feeds the calibration light. So this calibration light means, in every, if you want to calibrate, you need about 5 to 10 at least spectral lines on each order, in each order. So this is one order, this is another order like this, M order, M plus 1 order, M plus 2, M plus 3, like that. In each order, you need at least 5 or 10 or even more the better we require. So you need more than 1000 spectral lines overall between say 3800 to say 7000 angstrom. Okay, so how do you do this? Well, fortunately, we have like heavy atoms like thorium, uranium-238, and thorium. So these heavy atoms have have so many optical lines, and the atoms being these being heavy atoms, they are very stable in the time in terms of course they are radioactive, but if you make a discharge tube and put some argon gas or xenon gas, and then make the cathode out of thorium or uranium, and then apply voltage of 500 volt between them, then what happens is that the thorium evaporates from the cathode, and it emits the spectral lines, and it is extremely stable in terms of velocity, in the sense that they do not have a very large width, are very narrow, and since they are heavy atoms, their velocities are very stable, and so you can use them over years to calibrate the spectra against any shifts within the instrument or actual shifts on the stars. So simultaneously, we take these observations with the star and the spectral lines. In this case, these are thorium lines actually, and so this helps us to actually in situ measurements of the instrument velocity shifts, plus the velocity shift, actual velocity shift from the star. And once these observations are over, we take thorium or uranium on both the fibers. So you get before we take one calibration before or after the actual observation, and during the observations, the simultaneous calibration. By comparing these results, we can precisely measure the star velocity at a level of few meters or 1 meter per second by subtracting out the instrumental waves. Okay, so as I said that these are the samples of the stellar spectra. You can see so many spectral lines. These are all spectral lines. Now I want to tell one more very important thing is that we have to also know, because star is not a solid, it's a gaseous ball. So you have to make sure that like when you are trying to measure the wobbling around the star, you have to make sure that you are only taking care of using those lines that are strictly coming from the photospheres. Okay, because if you are trying to get lines that are coming from chromospheres or some other place where you have the star's own atmospheric velocities and all those things, so then you will not be able to catch the wobble of the star. The wobble of the star you can catch only if you are able to measure the photospheric lines. Unfortunately, the photospheric lines are very clearly defined. Most of them are iron lines, and you can see the iron lines here actually. These sharp lines are iron lines, and these broader lines are actually some gaseous lines. For example, this is H beta 4861. Okay, so because the H beta comes from many places, from photospheres, chromospheres, and many other places, so it is very broad. But if you look at the iron lines, they are very, very, very sharp. Okay, so these are from different stars of different magnitudes, and I think this one is slightly evolved star, and these two are main sequence stars. Okay, so this is just I wanted to show you the example of this kind of lines. And so what we are trying to do is that trying to measure out the Doppler shift of all these individual lines by cross-correlating against each other. I mean, by against each other means if I consider, suppose I consider this particular line at time t1 and then time t2, how much is the shift of this particular line? And what is whether this shift is same as this line shift with respect to this. If the shifts are not same, obviously it is not because of wobble, it is because of some other phenomena. So that is how we make sure if statistically we make sure that we are able to pick up only the wobbling and nothing else, and which means that we need so many lines, like more than 5,000 lines, and the lines have to be very sharp. Okay, so this is the cross-correlation technique I was talking about. So you have, suppose, this line to begin with, and then you have a mask which is moved like this, and then you try to figure out this mask. By moving this mask, you try to figure out that what is the shift in this line from between time t1 to t2 to t3 to t4, like that. And that's why you can went down to about a meter per second. Now the question is that if we can get down to 1 meter per second, then why not get down to 10 centimeter per second? I'll come to the next slide. Okay, before that, I want to tell you the one very important thing is that when you are doing this kind of measurements for spectral lines, from spectral lines, what happens is that the spectral information, this more number of lines you have, the more number of spectral lines you have. So it so happens that the maximum number of RN lines comes between around 4,000 to 5,000. Okay, after that it starts decaying. You can see these are the number of lines you get. Okay, so it is a K type star, this is the F type star, this is the A type star. So as the stars become hotter and hotter, there are fewer lines. But as you go, so suns fall somewhere here. So we can do this kind of radial velocity research only in those stars which has large number of lines. So, and that's why this region, that is from 4,000 to 5,500 or to 6,000, is the most useful region. So the error in the RV determinations is actually determined as 1 upon signal to noise ratio to the power of 0.5 multiplied with the wavelength coverage. That is, well, what is the length of wavelength we have covered, like from 4,000 to 4,500 or 4,000 to 5,000 or 4,000 to 6,000, like that. So the larger number of this thing is there. So you are basically covering large number of absorption lines, and hence it goes square root of that wavelength interval, and then multiplied by the resolution of the spectrograph. So yeah, the resolution goes high, of course, the more better it will be able to do. So this is what the sigma of RV is one can measure. Okay, and okay, so these are the first few results that we got early in 2010 from Paris. You can see that that with a standard star, like there are like some stars which do not have any planets, but they are very stable, and they are actually used to determine the stability of your plan of your spectrograph. You see, just as you know, when you try make something, you need some standard candle kind of thing by which you calibrate your spectrograph. Of course, we are calibrating against spectral lamp. That is fine, but then like you also need to calibrate your spectrograph against some standard stars, which over the time we have found that they are extremely stable stars, and they do not like they what you call they do not have any planets, but they are extremely stable in terms of seismology. That is, they don't pulsate much, and so they are quiet, and so they actually can be used as a as a uh, as a as a source to calibrate your spectrograph and demonstrate how stable your instrument is. Okay, so for example, with on tau sigma draconis, we are able to get over 2 years of 1.4 meters over a period of 2 years. So, which means that that the planet doesn't have a planet, like less than a Jupiter mass, or even a Neptune. Maybe Earth-like is there, we do not know. At the same time, our instrument is stable down to a level of 1.4 meter per second. Okay. Similarly, like there's another star called Tau Ceti, which people have tested to a level of with large telescopes, like with others, not large telescope, but with other spectrographs, which are a little bit more sensitive than ours, Paris. And for example, on this star, we got about 70 centimeter or 0.7 meters. They got about 30-40 centimeters per second. So which means that, like even though these are ways to, like demonstrate how stable your spectrograph is. Okay, so in 2016, we had an iteration conference at Yale University in US, in which all the stable spectrographs that are doing for planet searches were compared upon, and it was a 5 days conference that I also attended that. And then we presented our results, and finally a referred paper came out of it as a review paper. So as like circa 2016, these were the best spectrographs available in 2016, and in which I'm very proud to say that Paris stood third in that list. And you can see that for a signal to noise of 200, we are able to we're able to reach a level of 1 meter per second. The best, of course, was 80 centimeter. Okay. Now I come to the situation is that why it is so difficult to measure 10 centimeter or go to some meter. The reason is that when the starlight is dispersed, what we are trying to measure is we are trying to measure length actually. Okay, that is how much physically the line is shift on the detector. So now if you look at, which means that, like typical pixel size in a silicon detector is like of the order of few microns, a few tens of microns, like 15 microns. The 15 micron corresponds to typically will be 100 meter per second, or like 800 meter per second, or maybe kilometer per second, or maybe 600, depending upon at what resolution you are. If you are at 100,000 resolution, it may be 600 meters. If you are at 60,000 resolution, it will be around 800 meters per second. Okay, but we want to go to some meter, which means that you are trying to measure the shift in the line at a level of length you are trying to measure. That is, when you are measuring shift, that means you are basically measuring the length. Okay, on the detector, how much it is shifted. So which means you are like going to get down to a level of a nanometer level. Okay, it basically means that. Okay, and you see here, I can see very clearly that this is the silicon lattice. Okay, and it is a one nanometer scale here, and you have here 10 centimeter per second scale. That is few atoms, 1, 2, 3, 4, 5, 6, 7, around 6 silicon atoms length. Yeah, if you can measure, then you will be getting down to 10 centimeter per second. I mean, that's really, really very challenging. Okay, so that is where the problem comes, and that's why the 10 centimeter per second is actually still, what you call is eluding us actually. So the best now people have done is about 20, 30 per second or something, 30 centimeter per second. Okay. Okay. Now I would like to give a little bit more attention on the fact that, where we also stand our efforts, like on the development of the software data pipeline. When you do all these things, measure so much of work, build experiments, build instruments to build the spectrograph, stabilize it, and all those things. Then you get the data. So we have to check whether we have also, are we sure that, like we are also, like our data pipeline, data analysis is also to a level which we are able to be, are we not putting any, like doing error in that? So what we did is that a very useful exercise, I just wanted to show this to you, is that as I showed you that the half spectrograph in 2016 stood, first, and it had, it was able to demonstrate 80 centimeters. Subsequently, it went down to like 30 centimeters actually. And so, and its pipeline is very well established. So what we did is that we took half data. Instead of Paris data, we took half data. And then, we analyzed that data with our pipeline. Okay, by taking some few things. Okay, so I call it as my RV pipeline. Okay, so you can see half pipeline and my RV pipeline, and we get a similar results. Like in my RV, we get 156.5 centimeter per second. RV limit as 38.1 centimeter, and you get here 38.3 centimeter. Okay, now the sigma RV is here. What you see, 156. This thing is the total dispersion, and sigma RV inside this is the short-term what you call dispersion. Okay, so you can see that we are getting the same result. My RV pipeline, which is basically the Paris pipeline, is getting the same results within statistical error bar as that of fast pipeline published. So this actually shows that we our pipeline is well established and we can do it very well. Okay. So now the system characteristics, as I said, that post 2016, many huge spectrographs have come up along with halves, and so as I said that the target is to get down somehow to 10 centimeter or better. So this spectrograph has come up. Now they are still, like working on this, and it is not, started science observation as such, but it is on the engineering runs. And so this is what, like this is from private communication with some of my collaborators, because they are the PI of this instrument. And you can see that they have been able to reach to 30 centimeters over a period of, like 62 centimeters over a period of 1 month, and on a single night they can get 30 centimeters. So what one does is that you can see a dispersion of so many this thing, okay? And you can see this is, like radial velocity in meters per second, or sorry, kilometers per second. Yeah, kilometers per second. Okay, so what they do is that they actually, you can see the 16.6570 is that is a decibel place is 4 decibel precise after, because like you have to in order to go to centimeter level you have to do it at 4 decimal places after. So so these are the like data points on a single night with this thing, and they take the bean of it. So when you bean it, so they become a flatter line, and then that gives you a what you call a much low dispersion down to 30 centimeter per second. Okay, before I go. So this is what, say for example, you have 1 point here and another point here. So when you take the median of those 2 points, you get 1 point here. So these are 2 data points per night, and you take median point of these 2, or mean point of these 2. Similarly, mean point of these 2. Similarly, this mean point of these 2. Similarly, this mean point like 2. In the mean point of these 2. So then, like if you do not take mean, then the unmean sigma is 2.2 meters. But if you take the mean point dispersion, then you get 70 centimeters. So similarly for this source, we get down to level of, like for a 1 month period, 62 centimeter, and for a single night, you get 30 centimeters. Okay, now this is what is the current, so far I've been talking of what is the current scenario. And now I will talk about some of the discoveries that we made with Paris. Okay, this is the first exoplanet discovery, and which is the evidence of sub-Saturn. So this is the this is the Kepler transit curve. Now, thing is that according to IAU, International Astronomical Union policies, a planet is considered to be discovered if uh, if someone shows that the probability of false positive, that it is not a planet, is less than 0.1%. Okay, that is very strict rule actually. Okay, so therefore all these transit surveys that I have talked about, Kepler, TAS, and future in Plato, what happens is this, that this like this discovery then goes to the name of the person who actually proves that this planet, the probability that this planet exists is more than 99.9%. That is, the false positive is less than 0.1%. So how do you do that actually? One way of doing is this, that you re-observe the whole source against in the plan, like you find out that it, let us try to understand first what are the various uh, scenarios under which it can be considered as false positive. A is that like it is not a planet going around the star. It may be like a dim star, like a M dwarf going around a very bright star like a O-type star. Then it will you will get a similar kind of contrast, and you will get a similar kind of dip. Okay. Then it is possible that the star doesn't have any planet around it, but in the field of view, because as I said that these stars, when these surveys are done, they have a certain PSF, point spread function. So, so for example, Kepler has a PSF of 10 arcseconds. Okay. And so in that case, what will happen is that within 10 arcseconds, suppose there are two stars, but you will see it as one star because your PSF is 10 arcseconds. Okay, and suppose one of those stars, slightly fainter one, is an eclipsing binary, that is one star going around another star, and they will have some like light fluctuation or transit curve because it's a binary system. Okay, now but since that is faint and you have a star which is like which you are trying to observe, but you cannot distinguish them between these two stars, then what happens is that you see the signal of the eclipsing binary background star or foreground star onto this your target star, and it will mimic as if it has a planet around it. Okay, so what happens is that 50% like this goes away as false positive. So you have to show that there are no background or foreground stars like that. So what you do is that you take various observations with large telescopes or small telescopes or whatever possible way, and say that okay, you have to take a high resolution images so that there is no background or foreground stars or eclipsing binary system. Alternately, what you can do, you do spectroscopy. If you do spectroscopy at radial velocity, what happens? Like in Hindi, they say that दूध का दूध पानी का पानी हो जाता है, वैसा हो जाता है. क्योंकि क्या होता है? When you're looking at a particular star, which do spectroscopy, high-resolution spectroscopy, then what happens is that if the star itself is an eclipsing binary system, immediately you will know it's an eclipsing binary system because you will see the radial velocities of several kilometers per second. Okay, if it is a background star or a foreground star, obviously, like you are not pointing your fiber on that particular star, or you're pointing your target star only, and so therefore it gets delineated. Of course, the atmospheric seeing does come into the picture, and in case suppose the two stars are very close, like less than 1 arcsecond, then you may get into a problem. Okay, then in that case, you have to do a speckle imaging and show that there is no really less than 1 arcsecond, or there is no second star within 1 arcsecond of your star. Okay, so these are the various methods by which you can do that. So in this case, what we did is that we observed the source for over more than a year actually. Okay. And even though the period is only 19.42 days, and then because the star was, these what you call the star is quite faint enough for a 1.2 meter to do it. We needed a large number of data points, A, and B, we also needed to figure out this. The K value was quite small in this case. Okay, the K value was less than 1 meter, like 6 meters per second or something. Okay, so also therefore, like we had to really, like figure out whether that particular star this whatever radial velocity dispersion we are seeing is only because of the star, a planet around going the star, and not because the star is having some quakes or astroseismology or something. Because if the star is vibrating, there is a pulsating, then also it can produce a similar kind of variations. But those scales are of the will not remain periodic. They will be aperiodic and they will come and go. If the planet is there, it will always be there. Okay, so therefore we observe this source for about 2 years to make sure that yes, this is really a planet and nothing else. Okay, and so that's how this discovery was made finally in 2018, and then it was sub-Saturn, and it was a very difficult detection for us because considering that our aperture is very humble 1 meter telescope. Okay, now. So these are the things that I was talking about, the false positive probability that, like final probability, you can see that the planet probability is this, and other probabilities are extremely small, actually, you can see that. Okay, these are all 0, 0, 0, 0. Okay, and the planet is 0.981. Okay. Okay, now last year we had another very good discovery. It's called Hot Jupiter, and this was actually relatively simpler than the previous one. The reason is that it has a larger K value of the order of 70 meters per second, and it's also a larger 0.7 Jupiter mass. The important thing is that, as I told you, see, if you compare, before I come to this, if you compare the previous one, density was about 0.69. Okay, density was 0.69. Okay, while this one density is 0.31. Okay, and sorry, yes, 0.31, and it is very close to the host star, about 1/10 that our distance between Earth and Sun and Mercury. So you have a comparative charge. So this, Mercury position is beyond this scale. So that's why I put an arrow here. So distance is about 0.4 AU, and this is like, this distance is 0.05 AU. It is so close. Okay, and because being so close, it has its temperature is very high actually. It's around close to 2000 K. Okay, and of course, this was originally, suspected to be a planet by the TESS mission, and the TESS had a actually low cadence observation, so we had to take ground-based high cadence using our 43 centimeter telescope from Mount Abu, and then also we did this radial velocity mapping of the source for about 3 to 4 months, and we were able to prove that this is a planet. Note that previous one we had to do it for almost 2 years, while in this case in 3 months we came out. The reason is that its K value is very large, is about 70 meters. So the stellar jitters and stellar pulsation will not come to that level. So we were able to prove that that this is really a planet. So again, this was our second discovery. Okay, now I will come to the future. The future, what we in future we want to do, and as I told you that from 2016 to 2022 today, lot of advancement have happened. People are talking of going to sub 1 meter to detect massive Earths, super Earths around planets, around stars, which could be in the habitable zone. Okay. So obviously we have to go to the next, develop a new type of instrument, and for that we have to also have a new kind of telescope, modern telescope, So for that reason, we are having a new 2.5 meter telescope, and with which we will have PARS-2 as well. So currently the telescope is being built at Mount Abu, and we had PARS-2 is already made, but here I will discuss compare the PARS-1 and PARS-2. So you can see that the pupil diameter is double, and you have a different kind of cross dispersion, and the resolution much higher, 100,000, and the vacuum control is much better, the temperature control is much better. Okay. Okay, and also the input optics will be much better. I mean, we'll have a tip-tilt attached, that is, we will have also do seeing connections. You have the twinkling of the stars will be first order corrected, so that the stability with which light is input onto the fiber, 75 micron fiber, remains constant, and hence we get a greater signal to noise ratio. So not only like we will gain by doing this kind of trick. What we are doing is that, if we simply see the flux area, 1.2 meter to 2.5 meter, it's about factor of 4. Okay, but we want to gain over factor of 10. How do we do that? We correct the seeing also to some extent, so that the light remains focused all the time onto the fiber, and so that gives an added advantage, and hence we almost we are added advantage by 2, factor of 2 almost. So the flux difference is 4.5 or so. So almost 9 times more higher signal to noise ratio will get because of the the addition of the correction of the seeing along with the bigger aperture. So this is the schematic of that. Okay, this is the PARS-2 vacuum chamber design, optics design showing, and this is the temperature control simulations, and this is the actual spectrograph assembled inside this chamber, and you can actually see that it is now working at 100,000 resolution. Okay, and it is it will be the first light instrument for 2.5 meter telescope. Wavelength coverage is 380 nanometers, 720 nanometers. It is the highest resolution spectrograph in the country and one of the few in the world, and also first in Asia. Okay, so and in future we have plans to reduce the, right now 75 micron corresponds to 1.5 arcsecond on sky, but we want to have 1 arcsecond sky fiber also for bright stars, so that the resolution can be a little bit higher. So as I told you, as you increase the resolution, your radial velocity performance also increases, but at the cost of the lesser photons. So on bright star, definitely we can do that. So we are going to, in the near future, we are going to have another set of fibers. Okay. So now okay. So if you compare this optical ray tracing with these two off-axis parabolas and these two off-axis parabolas, the issue is here. Okay, the camera lens barrel, you can see this here, and the 6K by 6K CCD from E to V is here, and so like you have the whole thing is now working, and the temperature control system. And okay, this is the spectra of PARS-2 is here. I told you, as we take of course the telescope is not ready, so we have taken some solar spectra, because with sun you don't need a telescope. You have a small telescope, you can connect the fiber and you can get the sunlight. And this is the iridium argon calibration lines. You can see the entire spectra, how it looks like, and see the blow up is here. Okay, and then this is a resolution. You can compare PARS-2 resolution with PARS-1, the same spectral lines. You can see how beautifully it is resolved with respect to PARS-1. The difference between 100,000 and 65,000 resolution, and it is very beautiful actually. Okay. Okay, so what are the PARS-2 target parameters? So we have goal is to go down to 50 centimeter or better. Okay, and basically, what are the issues here? The issues are I can say that you have stellar oscillation. I was talking about layers, granulation of the order of like few meters, everything at a level of few meters or sub-meters. So, but all these things, if you keep taking observations like a long time, like for the sub-Neptune, we had to take observations for two years, and we could negate many of these other source of oscillations from the star, smooth them out and take the planet signal. So these are the things that goes in taking more. The more number of data you have, the more is better that you have a better statistics to ensure that yes, this is a planet and nothing else. Okay, so cadence is very important, and so typically for the k value, the amplitude is like k divided n is the total number of observations, and which directly goes down to RV of the RMS and multiplied by the square root of the total number of observations. Okay, so now what happens is that this is my very favorite slide. You can actually see this is a single photon noise limit measurements of the order of 20 centimeters to like 100 1 meter per second, and this is the minimum survey time in years. Okay, so if you have say suppose if you have say 50 centimeter, if your single photon noise you have 50 centimeter 50 centimeter per second your noise level, and then like you can see that you can if in 1 year time you can in few years time you can get down to a level of actual detection of 50 centimeter per second k value. Okay, say in 2 to 3 years time. So that is if you select your target, at a like let us say like 100 targets, and keep observing for a year at a level of 50 centimeters, then you will be able to like detect at least a few planets around the habitable zone. Okay. So this is what the habitable zone is. So 50 centimeter means somewhere here. Okay. So this 50 centimeter comes here, so around m dot. Okay, if you want to go further down like 40 centimeters, then you will go down to k dot. So like that. Still you see Earth is very far away. So that's why you can only go there if you are around, if you touch 10 centimeter, which is little bit far from us. Okay. Oops. Okay, as you see, notice that this simulation was done for a 4-meter class telescope for a hypothetical program called HABEX by these authors. So what I did is the collecting area ratio between a 4-meter and a 2.5-meter aperture telescope is that of 2.56 meter, 2.56. So therefore, we are basically 1 magnitude below the 4-meter capacity. So what is achievable up to 9th magnitude star, we can do the same thing on a 8th magnitude star on a 2.5 meter telescope. This is what we have been able to show here. And here again, you can see that with a systemic floor noise of 50 centimeter per second, you can be able to achieve about 30-40 centimeters green color here on an 8th magnitude star. And this is a very sweet place here for us to discover planets somewhere here in this region somewhere. Okay, now this is one of my last slides. It's like a few minutes video showing the Paras-2 spectrograph, how it looks like actually, to give you an all idea, because everyone cannot visit Mount Abu and it is a temperature control system. One cannot go actually see it. So I thought, I will just show you this video. It's a few minutes video. So the spectrograph is inside a vacuum chamber, and this is the vacuum chamber is open and it's on a rail actually. The optic table is on a rail. So now the rail is closing actually. The vacuum chamber is closing. It's motorized. Here you can see the detector shutter actually. Detector is inside. And you can see the fiber cable, two fibers, one star and one calibration, the blue fiber. And the end part of the detector, this cryogenic part of the detector. And this is the blue fibers. So these are two of my engineers. So the human figure will give you an idea of the length of the spectrum. Okay. Okay, this is my last slide, and I want to give very special thanks to the present and the past directors of PRL, because without the present director and the past director, it was not possible to conduct this kind of experiment at PRL, which began in 2007, and then continued, is now continuing with a greater enthusiasm and with a much greater, what we call. I don't know what to say. I'm very great. We are very excited actually that like with this Paris too. And so for all these things, without the director's help and without the DOS help budget and so many people there, like I would thank PPG chair also for this, and so that, so that that's all I have to say. And I also thank my collaborators, international collaborators, team members, both at Ahmedabad and at Mount Abu. The observatory staff is excellent. Without them, it's not possible. So that's all I have to say.
Thank you, Professor Abhijit Chakraborty, for this excellent exposition of what is involved in doing these challenging experiments, the type of the designs that you have made. You talked about the kind of first light and discovery kind of lights that you have observed through this telescope, and the and then the future works that you are planning with the 2.5 meter telescope and the upgraded Paris designs as well. It's been a very wonderful journey all through that you have carried out over the past 15 years now, and then very nicely put forth here. Thank you. And I'm sure there will be questions on this topic, some curiosity words and some more technical questions. So first I would like to invite questions from the WebEx panel panelists, or anyone who is looking in the WebEx. Maybe I will request them to raise hands in the feature that you have on the WebEx, and that will help me in identifying the speakers. There are several on the WebEx here. So I see the first raised hand from Professor Anil Bharadwaj. So I would request Professor Bharadwaj to go ahead and ask his question or make his comment.
Thank you, Pallam, and thank you, Abhijit, for a very excellent talk, summarizing all the nuances as well as challenges which is faced during developing such a instrument and then making observations. So I'm asking this question for a larger audience because they must be feeling how much time it would really take to really confirm two observations, night after night, to say that it is an exoplanet. So typically, how much time it takes? Whether it takes 1 day, 2 day, 1 month, or 1 year. So can you just throw some light on that so that audience who is there on the YouTube as well as WebEx
Actually,
get enlightened?
Actually, this is a very good question. You see, as I said that the first planet we had to observe for 2 years because the K value was very small. So that some few thumb rules are there that if you are at like 10 sigma level, that is, like your sigma is 1 meter per second, and your K value is let us say 10 sigma or even greater than that, then you don't need much time actually. You probably will require about and suppose the other thumb rule is that you need to observe at least 3 periods. Like suppose your period of the planet going around the star is x, then your observation should be around 3x kind of thing, period of time. Okay. So if it's 2 months of 2 months, obviously straight away it goes to 6 months. Okay. So these are the like if you're at a level first, this is about the 3x first criteria is 3x. The next criteria is your signal to noise criteria. Okay, these two criteria actually complicate the situation. Plus the other criteria is that if you are trying to detect a planet less than 1 meter or close to 1 meter, then it becomes you are in a completely different ball game. What happens is that at that level, you not only the planet, you have several other things that are coming into the picture, like the stellar noise, which is stellar. I am talking of noise because for us it is noise, but for someone doing stellar astrophysics, that is signal for him. Means the stars also pulsate. And for using star pulsation studies, one can determine the health of the star, that is the age of the star and the evolutionary sequence of the star, what is happening inside the star. So, so they actually interfere in detection of the planet. Okay. So because they are also at the similar level, but they are not periodic. They are periodic. They come and go. But if the planet period remains fixed, so typically that's why in the first sub-Neptune we have to observe it for 2 years. A is that our the K value was around 6 meter per second, and our detection was at a 1 sigma level. Okay, because it was a fainter star, so our error bars were all the order of between 6 to 10 meters per second. So how to do with a 6 meter with that kind of thing is that we have to take many data and prove that you are able to still get the like the get the RV curve without like if it is not due to planet, then you will not get the RV curve over 2 years of time. It will vanish actually. So that is so I hope I am able to answer the question.
So what I understand from you, what you're telling for a layman, depends upon the magnitude of the star in terms of the light, but also depends upon that you should see it 3 rotation or 3 revolution of a planet around the star, minimum. And for that itself, depending upon how much time it takes, you have to wait for that long, and you will not be able to observe it every night, depending upon how good the quality of the night is.
Exactly.
So that's how
this is a tough field actually, to tell you, because there is a serendipity. Plus, many times you may ask that we started this, why it took going up to 2018 to discover the first. The reason is that we were pretty unlucky in the middle. We looked into many stars, and they all turned to false positive. I mean, the Kepler showed very nice curves, but when we looked into it, they were not planets; they were something else. Okay, so So this is
I have,
serendipity, and you have to there is some fate involved in the serendipity. The right word is serendipity.
I have another small question, and this is the last question from my side. And that is a little to do with the future of astronomy, particularly ground-based. Now we are, as you know, many satellites are coming up in space, and more so particularly for communication.
Yeah.
And the number is going to increase exponentially. So with so much number of satellites in space and going to increase further, is that be a challenge for ground-based astronomy?
It is a challenge for ground-based observations. The reason for that, is that we have, particularly for doing photometry. Suppose when you are doing transit photometry from the ground, and suppose in the field this fellow comes and crosses over the star. I mean, probability may not be very high, but there is certain probability. It's not zero. There is a non-zero probability is there. So then, of course, that particular data goes west, and you're for those, because every few seconds you are taking frames, so those frames will go back. Also, it may affect if the satellite is bright enough, it can affect your analysis to some extent. On the radial velocity side, unless because here you are actually looking the star and nothing else. So unless the satellite is actually eclipsing the star, it will not affect it.
Okay, thank you, Abhijit.
Okay, thank you. Next, I see Dr. Prithul Desai's hand up. So, Dr. Desai, please.
Thank you, Professor Chakraborty, for giving an excellent talk. Sir, I have one question. Whatever detection we make is through this RV method, where the planet is in the line of, supposed to be in the line of sight.
No,
So
not from for the RV method. The line of sight is not necessary. If it is not line of sight, you will measure M sin I, but you will still see it.
We will still see. But for example, if I have a planet outside the in the line of sight and not in the same plane, for example, do we have any methods where we can detect the presence of exoplanets in that case?
No. I think you have to understand the situation like this. The radial velocity method is slightly different compared to the transit method. In transit method, it will only transit if it is in the line of sight. In this case, you are getting the light from the star. Irrespective of what is the orbital plane inclination with respect to you, you will always see the radial velocity variation with a magnitude equivalent to M sin I. The sin I factor comes there. That's all. You'll always see it. Unless the star is pole on, that is, you are looking pole on, then of course, because then I becomes zero. Then sin zero is you will not see.
Yeah, it becomes infinite.
Yeah, that is what.
Okay, sir. Thank you.
Okay, thank you. Next, we have a question by Professor P.K. Ahluwalia. Yeah, please go ahead. Ask your question.
Very much. I enjoyed your talk very much, and I think it was excellent. And you know that among students also, looking at the sky is the most enchanting thing. And if you ask any school student, they will give you that they would like to study stars and planets and galaxies and all those things. My question is this, that are we really looking for some kind of an extraterrestrial life by looking at the exoplanets? Because sometimes we say that their position is such that it is very similar to what is the position of the earth compared to the sun. Will your work also throw some kind of a light on this aspect also, that possibly or probably this is the exoplanet where you can look forward to life as it exists on earth?
Well, right now, of course, the ultimate aim of doing exoplanet research is that only. Okay. However, before we look for, there is something called Drake equation. I don't have it on this slide. Otherwise, I would have shown it. The probability of having life, as per Professor Drake, is like 1 in million, exactly 1 in billion times. Okay. So, so basically, but before we go there, we have to first find out planets in the habitable zone. That itself, out of 4,000, we hardly know few, and they also, none of them actually fits well with the Earth scenario. Okay. Okay, because I will tell you the problem is basically, like when you do transit, you are slightly biased in the sense the closer the orbit of the planet, the more probability that it will transit. Okay, okay, orbit that is at a Mercury distance. Okay, is like in an angle it will there will be more what you call probably that it will probably that it will transit.
Okay.
So that's why we are discovering close-in stars more than those planets which are in the habitable zone. That is one thing. Secondly, as I told you in the RV, this thing, getting down to 10 centimeter is still in a dream on a regular basis. Okay. So unless that happens, Earth twin will be very difficult to detect. But I think, it may happen that in the near future, with the advance in technology, ground-based 10 centimeter will be possible. I'm hoping in the next decade or so. Okay, then the scenario will change a little bit.
Okay, thank you.
So right now our aim is to find out planets in the habitable zone.
Okay. There is one more supplementary question to this actually.
Yeah.
With the coming of the new education policy 2020, this national education policy, students are being asked at the undergraduate level also to do some kind of research projects. Now, the kind of data which you are collecting, is it possible to share with the students and analyze it to detect something so that they can really use that data and analyze it and have a feel of what is actually happening? Because the kind of precision with which you are working, that's just mind blowing. You said that the probability has to be less than that
0.1%.
difference 1%, less than 1%, if I am saying it right. So how can we really bring that audience also to have the feel of what happens at the level of this kind of research, which is very exciting also?
See, first of all, like in US, NASA is employing this. Okay. See, for the radial velocity, it is little bit difficult. But for the satellite survey programs, like for the Kepler or TESS or future Plato, because that is going to generate a huge amount of data sets over the entire sky. And those analysis can be done easily through standard programs. So all you need is a computer, and then download the program and then you run it. Or you can define your own code in Python or C, C++, whatever. Okay. No, you have to understand what it is actually, of course. Okay. That kind of work is being done even at a college level or school level in US. Okay. So, so that is possible. Okay. For the RV, it is a little bit difficult because RV is really a little bit more complicated than simply photometry analysis. Okay. So in future, if we have, like photometric satellite surveys, like our own photometric satellite surveys, like TESS or Kepler, then definitely that's a good thing to look into and then employ the students from schools and colleges.
Thank you. Thank you very much, Professor Abhijit.
Okay. Yes. Before, I think there are no more raised hands here at present. So I'll first go to.
There is one from Manush.
Yeah, I'll come to him. Yeah, I'll come to him. But there is another question from Astros. No, this is from Professor Ambasta. He's asking any astroseismology work planned with your instrument?
Hello, who asked this question?
This is Professor Ashok Ambasta.
Okay. Hi, Ashok, how are you?
Oh, yes, I am all right. Yeah.
Okay.
It was
Yeah,
great to.
like we don't do like that, but with panels too, like when it becomes operational fully with the 2.5 meter, I actually told, I think someone from Udaipur Solar Observatory, if anybody wants to do stellar seismology, they are beginning to take the data, they can take it and do it.
Okay. Yeah. So actually, the kind of measurement, in radial velocity, which you seem to have, the improvement in the accuracy, precision, and all that. So I was wondering, that because of the size of your telescope and also the measurement accuracies, this may be interesting aspect, because so far we have been doing a lot of work on helioseismology from Udaipur Solar Observatory, and there has been extension of that to stars. So that is why I asked the question whether you have any plans to.
No, we have the data. We will have the data. If someone wants to use it for them, we'll be ready to give.
Okay, great. Yeah. So congratulations for your new instrument, Paras 2. A lot of work has gone into
Thank you.
a lot of hard work. So congratulations to you. Yeah. Okay. Thanks.
Okay. Thank you. Yes, Dr. Kamal.
Hello.
Yes, ma'am.
Yeah. My question is that most of the exoplanet we have discovered so far is around M stars. While
No, that's not correct.
Isn't it?
No, that's not correct.
So, basically the low mass red dwarfs, right?
Low mass red dwarfs, there are some, but most of the planets that we have discovered are around sun-like stars. G and K stars. Because M dwarfs are faint, and so like usually like most M dwarfs, the closest M dwarf is around, I think, 8th or 9th magnitude. So the majority of the M dwarfs are like they are fainter than 10 magnitude. That's why with Paras 1 on the 1.2 meter, we cannot ever touch them because we cannot go below 10 magnitude. So with the 2.5 meter, we will be doing M dwarf profiles. Okay, so this is true for everywhere. So so M dwarfs, people are looking to stars or planets around M dwarfs, but for that you need at least like 2.5 or 3.6 meter or 5 meter telescope, larger.
Yeah, that's my question is.
Chunks are basically around 12 magnitude actually. 12 to 14 magnitude, they are huge number of.
Okay. So that's basically the habitable zone is size of the habitable zone is divided by, basically defined by the input flux from X-ray or UV photons from the massive stars or host stars.
The habitable zone is defined as I said, that it is defined as the temperature should be between -50 to +60 or something like that. Assuming that that there is no atmosphere on it. Okay, that's without the atmosphere. Then you put the atmosphere and then you manage how it is done. So now you have to show that like just star flux on it. What should be the distance between the planet and the star? So M dot will be the problem with M dot habitable zone is one thing that that the end of habitable zone is such that like it is within the tidal locking zone. That is, when the planet is tidally locked with respect to the star, what happens is the one surface of the planet is always looking towards the sun. It's like in the moon and Earth system. The moon is tidally locked with the Earth, so it one side always looks at it. So in that case, what happens is that you have, like very high temperature on one side because day side is always there and night side is always there. So what happens is that very high temperature on day side and very low temperature in night side, even though it is in the habitable zone, then people talk about like some kind of activity within the twilight zone. So that becomes a little bit, like over ambitious, I think. So, I didn't go into all those details in this, but my personal feeling is that best thing to look into habitable zone is around 8 dark stars where the planets will not be tidally left with restricted distance. And so therefore, one can go look into there actually. But only thing is then in that case, your sensitivity, RV sensitivity has to be below 50 centimeter, maybe about 30, 40. That's why first thing that people are trying to do is around 30 centimeter.
Okay, okay. Yeah, thank you. Thank you for the clarity.
Okay. Yeah, we have one YouTube question here by Rahul Patak. He's asking what are the differences between the CCDs used in Paras 1 and Paras 2 as per signal sensitivity measurement.
See, the Paras one is 4K by 4K, that is 4096 by 4096, 15 micron pixel CCD. There is not a significant difference between the two. But in terms of pixel size and the way you read out and how the way the controller electronics work, there is a difference in terms of size because the Paras 2 uses a 6K by 6K, which is a physical size of 92 millimeter by 92 millimeter, and this is the largest possible detector you can get today by technology. Okay, and this is the same detector that is being flown for the Plato mission. The reason we chose this is because of very high extreme sensitivity of this, apart from the low noise level, and also like its quantum efficiency is quite high. Of course, the Paras 1 quantum efficiency is also quite high, but the 6K is less noisier than the 4K.
Okay. Yeah, at present I don't see any more questions, but I have one, which is when you were answering to some earlier question, you said that there were several false positives because of which it took more time for you to come up with a real discovery with unambiguous way. So, okay, for the general audience, can you just throw light on what are all these other things you said that which contribute to the false positives?
Yeah, so most of them turned out to be eclipsing binary systems. Secondly, they turned out to be like just some kind of background or foreground stars. Okay, and light being contaminated. One thing what we do is that we typically we do line bisector analysis, by which by doing that spectral line bisector analysis, that is the first exercise I do whoever joins me for PhD. Okay, so the line bisector analysis tells us whether there is a contamination, light contamination is there from neighboring star, or there is some issue with the stellar seismology. Okay, so we have actually observed so far about 40 to 50 stars. Okay, and as I told you, most of them are gone because they are like many of them were not transiting, but initially when the Kepler data was not out, we were actually blindly looking for planets to some extent up to 2013 or 14. Okay, later on we started looking into Kepler, then K2, and now TESS.
Okay, thanks for that. And are there any more questions on this WebEx panel? And also, I'm not seeing any questions on the YouTube. I think you have taken.
There is one question recently posted.
Okay, please go ahead.
Daniel Portia, and the question is: will we ever take pictures of exoplanet with virtual reality?
Well, I do not understand what he means by virtual reality. Pictures of taking, as I told you, the pictures of exoplanets, because the contrast level is so huge, it is basically not possible. As we understand picture of taking stars. With JW60 going up, that in the mid IR, at 20 micron, it is, if one tries to do some coronagraphy, okay, there was a proposal with JWST is that in front of JWST you fly another small satellite, and then you block the star, and then with a we block it like a like a coronagraph with the shape of the coronavirus should be like a flower petal kind of thing. I mean, there is exact science for that. I cannot explain it on this talk. But if you do that, then maybe you will be able to get down to 1 million or 1 million time contrast level. Then you can see the planet. Okay. Now, question is that if you do it at 10 micron level, at the 10 micron level, because the star will be emitting less because of the black body, you are in the Wien's law, Rayleigh Jeans area, where the star black body is getting down, where the planet itself, because of the heat it receives from the host star, it is emitting in because, for example, like Earth reaches maximum at 10 micron. So the planet will be brighter enough. So the contrast scenario will change. So it is possible that JWS to may be able to do through this kind of coronavirus. And then we may be able to see the planet image in 10 micron.
Okay. Okay. I think with this, I think we come towards the end of this. I would like to first, thank Professor Abhijit Chakraborty for this excellent.
It was my pleasure.
Excellent talk, excellent work that you're doing, and I think you have answered. There have been lot of interactions. You have answered all the questions, and that the audience had. It's been a pleasure having you and deliver this, the fourth, PRL IAPT Dr. Vikram Sarabhai lecture. Thank you very much. Okay. So we would, yes. So moving on, I would now call upon Professor P.K. Ahluwalia. He's the National President of IAPT, and Professor Ahluwalia is an ex-professor of physics at Himachal Pradesh University in Shimla. He is actively contributing to the physics education research. And with this, brief introduction, I will now request Professor Ahluwalia to make his remarks, as the IAPT chairperson, president, to make your remarks, please. So,
Thank you
Professor
very
Ahluwalia.
much. Thank you very much, and good afternoon to everybody. As I mentioned earlier, also I really enjoyed this lecture very much. And these days, because PRL is also celebrating its Diamond Jubilee, I would like to greet you all for this very special occasion. I would also like to tell you that these days I am watching Rocket Boys, the serial which is coming on the Sony television. And that was really wonderful to see. I have seen 4 or 5 episodes of that to know how Vikram Sarabhai's thought process about Atmanirbharta was actually playing in his mind. And there is a very contrasting role which is being played by Bhava and Vikram Sarabhai at the same time, almost at the same time. And I think there is a story which must be shared with a wider audience. Professor Anil is here. I would like that, sir. I think for IAPT audience also, you can draw such programs which we can carry forward to about 10,000 members of IAPT itself. That will be wonderful. And, this lecture particularly was, meeting a scientist who has made a real discovery. And that is something at the level of the universe, if you allow me to put it like that. And even these stories also need to be shared with the students. We must excite them to bring the excitement for studying science, particularly STEM area, which we are talking about, in a big manner. And that is our endeavor also. And maybe, sir, I don't know whether uh, that is possible or not. If your scientists can create some kind of podcast, for example, Professor Abhijit can talk about maybe in 5 or 7 minutes in a small podcast about exoplanet. What is it? What was his excitement about the discovery which has been made? And his lecture was also telling us the challenges, which were there. And the way such, state of the art equipments are created, conceived, and, made available so that something of which we can be proud of is done. I think these are the stories which need to be, at least in the Diamond Jubilee year, these must reach the big audience. And maybe that there is something at the back of Rocket Boys, which is the inspiration is coming from PRL itself, and that is why we are seeing that serial. IAPT is always such ready for such thing. I was even mentioning one thing more, sir, when I was discussing this with Professor Joshipura, that when this lecture has been finished, this is recorded, it is available on the YouTube also. But IAPT can also went ahead with something in a collaborative manner. We can create a quiz out of this lecture itself. And that quiz can also be, used by our regional councils, where this lecture can be shared because it is a reusable object now. Anybody can switch it on and start listening to it. But followed by, because the intensity of involvement and the engagement, if it has to be increased, by a small quiz. That will be a wonderful thing. When I actually started looking at Professor Abhijit's lecture title itself, I went on the internet and I saw that they were talking about some quizlets on exoplanets itself. So I think if those kinds of things can be brought about into that interface between PRL and the young audience, I think that will do wonderful things, and they will create new excitement among students, particularly young students and young research scholars. I thank you very much that IAPT has been for the last 4 years now been conducting this very special PRL IAPT Vikram Sarabhai lecture series. And we look forward to more such interactions, sir, maybe more such ideas. Thank you very much that you have become our institutional member also. I would like that you should also become our life members, sir. I don't know whether you are there or not, the audience which is sitting here, because even that helps us in a very big way. That brings us some amount also, so that we can carry forward our projects which we are trying to actually do. I have all the appreciation for the effort which Professor Joshipura has put into it, and the Gujarat REC which has done. And he always excites us, Joshipura ji. And because he is sitting in Ahmedabad with your great institution so nicely available, I think we look forward from IAPT side some great collaborations. Maybe the way I was talking about those student projects, because people ask us, sir, अब student project करवाने हैं तो क्या करें हम इसके लिए? Otherwise, what happens is, they will be doing all those repeated things, copying one thing from here and doing something there. Can we really bring all those things in parallel with the thought process which has been put out in the new education policy itself? I once again, on behalf of IAPT, express my gratitude to Professor Bhattacharya, Professor Chakraborty, Professor Abhijit Chakraborty ji, and Dr. Joshipura, Professor Anil, and all the members, the Dean Sab, Professor D. Pallam Rajuji. Thank you very much for giving me this opportunity personally. And I think we are going to use this lecture to excite students. Once again, thank you very much. And please keep on interacting and collaborating with us. Thank you.
Thank you, Professor Ahluwalia, for your appreciation of the work that is being done by PRL and through this joint PRL IAPT lectures, and also sharing with us the national level activities. You spoke like a teacher. You said that you have to have quiz done later for the students. So I think I can see the teacher in you showing up how we can utilize any of given item or product to educate the children, and so very nicely, I think it's a very good idea. and definitely I'm sure the RC members will be taking note of it to encourage the younger students in school levels and college levels that will motivate them to listen to the lecture more carefully, and because the questions are there, it's an open book question, so type of question. So I think it's a very good idea, and very other points that you have made. I think it's very noteworthy, and I'm sure that will be going a long way to encourage the physics education and learning in India. Thank you very much. So now I'll invite Dr. Pruthul Desai, Secretary IAPT, Regional Council 7, which is Gujarat sector, and he is also a principal of Sir PT Science College in Surat. He'll be proposing the vote of thanks. Dr. Desai, please.
Thank you, Professor Pallam Raju. It's a matter of honor and proud privilege for me, Dr. Pruthul Desai, Regional Secretary RC7 IAPT, to propose a vote of thanks on this momentous occasion. At the outset, I wish to mention that today's lecture was fourth in the series of joint PRL IAPT Dr. Vikram Sarabhai lecture series, which is the brainchild of the Honorable Director, Professor Anil Bharadwaj. I thank him from the bottom of my heart for initiating this amazing series and personally nurturing it. I also thank Professor Bharadwaj for his wonderful and apt opening remarks, which set the ball rolling for today's program. His presence all throughout speaks volumes about his commitment for physics education. I thank you, sir, from the bottom of my heart. I would also like to thank the PRL, Professor Pallam Raju, who took all the pains to work out the modalities of this wonderful program and deftly anchoring the entire program. Sir, we have been fortunate to have a distinguished speaker of eminence and fame today, a person who himself discovered an exoplanet. Your lecture, sir, was directly coming from a horse's mouth. It was really indeed privilege for all of us to have listened to this wonderful and exhilarating talk. I thank Professor Abhijit for accepting our invitation and delivering an enlightening and exhilarating talk on this very fascinating subject. An animated Q&A which followed the talk unequivocally shows that the talk was enjoyed by all and has aroused interest amongst the audience. We have been fortunate to have Professor P.K. Ahluwalia, National President of IAPT, for sharing his words of wisdom on this occasion. Sir, you motivate all of us by your esteemed presence. A special thanks goes out to Professor Joshipura, immediate past National General Secretary of IAPT, who has mentored all of us and has been motivating us to carry out such activities. Sir, your valuable guidance is highly appreciated, and I thank you for all your help and guidance. I would also like to thank Professor Vinod Kumar, Regional President RC7, for his valuable guidance in arranging this program. The presence of gamut of faculties from PRL and other institutes, universities, and colleges is a big source of motivation for us. I thank all the faculty members for gracing this occasion. A program of this magnitude would not have been possible without proper media coverage and other technical assistance. A special thanks are due to Dr. Bhushit Vaishnav from PRL, who took pains to prepare the announcement flyer for this program and working out all other required logistics. I would also like to extend my gratitude to Dr. Vishal Joshi, PRL, who handled and coordinated YouTube plus WebEx for an interesting and thought-provoking Q&A session. Last but not the least, I am thankful to all the students and other interested participants for their attendance and an animated Q&A session. Your presence is a source of motivation and prods us to do more. Once again, I thank one and all from the bottom of my heart. Thank you.
So, okay, thank you.